Okay, we're continuing on here talking about chemistry. We were talking about buffers last time. So a couple reminders, a buffer. Buffer is a solution that will, again, resist changes in the pH, even if you add more acid or base to it. Remember, it's not necessarily a neutral solution always. It can be buffered at any pH, as we saw, for example, when we did the experiments. You had a buffer of 4, a buffer of 7, buffer of 10. You can really make a buffer at any pH you want. The deal is, wherever it is, it will basically be able to maintain it without really large jumps in pH, even if you continue to add acid or base to it. You will see little sort of increment jumps upwards or down, depending if you add acid or base, but you won't see a really giant jump in the pH. And that is because it is made up basically of one of two things. It's either a weak acid and the salt of its conjugate base, or it is a weak base and the salt of its conjugate acid. And that's really important, as we talked about, to how a buffer is able to function. It does have both of those things in the solution to begin with. So essentially speaking, it has a acid part to the buffer, and it has a base part to the buffer. And that's really how it's able to function, because when you do add more acid to it, it will react with some of the base part, but as we talked about, it will then make some more of the acid part of the buffer. And we'll use up a little bit of that base part. And if you add some base to it, it will react with the acid part of the buffer, but it will make the base part of the buffer. So it sort of always will generate part of the buffer in the action of it reacting. But there is a buffer capacity, as we also talked about. Again, if you add too strong of an acid or base, too many moles really, you can blow right through either your acid part of your buffer or your base part of your buffer, and it will no longer be able to act as a buffer. It really is able to do this because it pretty much prevents one of two things happening, depending on what you're doing. It prevents the formation of free H plus in solution when you add an acid, and it prevents the formation of free OH minus in solution when you add base. And that's important because those things are related to each other. As one goes up, the other goes down, and vice versa, obviously. So by preventing any more free H plus in the solution or any more free OH minus in the solution, it basically allows the H plus concentration that you started with to remain relatively constant. And that's really why your pH stays relatively constant. And the reason it has to be a weak acid or a weak base to do that is it is a weak electrolyte. It will be able to set up that equilibrium, and it basically will be able to keep both parts of the buffer in solution. You cannot achieve that with a strong acid or a strong base, because it will 100% break apart, and you'll either have the conjugate acid in solution only, or you have the conjugate base in solution only. You won't have a way to keep both the acid part of the buffer and the base part of the buffer in solution together, which again, as I mentioned, is essential to how it functions. These are really common ion type of situations, as we also talked about, and really there is an equation that's really important, which is the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is really the equation that we use for buffers, and it really is the only place where you should use the Henderson-Hasselbalch equation. You do have two options. Because it is a buffer and there's not going to be a very large change from initial concentrations to final concentrations, you can use the initial concentrations and go directly into the Henderson-Hasselbalch equation and make sure that you do solve for the pH of the solution. Again, the pKa value here being minus the log of the Ka. You also have still the option, if you want, instead of using the Henderson-Hasselbalch equation, you could still use an ice table. The importance of, if you do use an ice table, is you got to have that initial concentration on the product side of the common ion. Otherwise, you are not doing a buffer problem. You're doing either a weak acid problem or a weak base problem. So you can do either one. They both technically should come out exactly the same. It's just whatever your preference is. But definitely you should not overuse the Henderson-Hasselbalch equation in situations that are not a buffer situation. So if they're not a buffer situation, then you definitely should not use it. The other important thing that we did talk about as well is the idea of when we add, I'm not sure how to draw that, volume to volume, I'm not sure. So when we add volume to volume, it's important to do the ice table in moles. As moles stay constant, they do not change, but the molarity does change as you add volume. So whenever we have any situation like we did, I think on a couple of examples here with the buffers last time, you add some acid or base to your buffer, or like you did in the lab the other day when you added some acid or base to it, you do need to do an ice table. And really the purpose of the ice table is to figure out how the concentration of your weak acid and conjugate base in your buffer, or your weak base and your conjugate acid in your buffer, change as a result of adding the acid or base. So you do need to do that first ice table in moles, and then you should really convert it back to molarity at the end of the first ice table. It's really good practice to do that. And that happens with any time we are adding volume to volume. You got to kind of do it in moles. And at that first ice table in moles, usually in that situation, you know what the change is going to be. So we don't use X's usually. We will use actual numbers. And remember, the simple way to remember it is you cannot have a negative number. So go with the smaller number as the change one that you need as you go across the change part of it. Any questions on buffers? Yeah. It means it has a spectator ion on it. So for example, acetic acid would be the weak acid. Sodium acetate would be the salt of its conjugate base. Its actual conjugate base is acetate ion. What makes it a salt is its ionic compound. That's what a salt is, just an ionic compound. So it has this sodium ion there to balance out the charge. So that's what it means. The salt part, are the ion that's really there just to balance out the charge, not really doing much, but going for a swim. It's really like a spectator ion. In this case, it's really the acetate part that would be the functioning part of the buffer. The sodium is just there to hang out. Sodium's not going to do anything with the pH anyways, right? Because it is a neutral salt, right? So it won't do anything to affect the pH. Other questions on that? Okay, so the next topic we're going to talk about here is everybody's favorite thing, which is titrations, I think. So, okay, the wrong way there. We'll go this way. All right, so we're going to talk about titrations. Maybe there it is. That's the slide I'm looking for. So we're going to talk about titrations. When we do a titration, we do typically add a solution of known volume and a sort of solution of unknown volume. So there's usually sort of a known solution that we're adding and an unknown solution. We use a burette, as you might be familiar with. So for example, you can put something like sodium hydroxide up there, which is a base. And maybe down under here, you got something like HCl, which is an acid. So you may know the concentration of the base, you may know the concentration of the acid, but one of those you do not know. So typically we do a titration. A lot of times we put a titration till we reach what is known as the equivalence point. And you typically want to titrate till you reach the equivalence point. And that is actually the point where, and really important, it is the point where in the case of an acid-base titration, the moles of the acid will exactly equal the moles of the base. So that is pretty much the equivalence point. You typically want to stop your titration at the equivalence point. Sometimes people call the end point of their titration just that, the end point. The end point's where you lay up your titration. And if you do a good titration, your endpoint and the equivalence point should frankly be pretty close to each other. You don't want to lay it up too early. So how do you know when you should stop? Perhaps we use an indicator, and we've used some indicators in the lab already, and you've used them before. That is our favorite one right there, phenolphthalein, perhaps, yeah. Phenolphthalein is an indicator you probably used last semester and probably familiar with, and we used it a little bit this semester as well. Phenolphthalein is what color in acidic solution? Yes, it is colorless. And in neutral solution, it is? No, it's still colorless. Yeah. In basic solution, it is pink. Yeah. You guys had the coloring crayons the other day, didn't you? So it is actually pink there in basic solution, or super pink, depending on how your titration skills are. And that is because most indicators work over a pH range. So something like phenolphthalein is like an 8.3 to like 10-ish pH. Around 8.3, it's actually colorless. And then it gradually gets some pink color to my favorite, super dark pink in that area of the pH sort of range there. And you're usually yelled at right by your teacher that you want to stop when you get the lightest shade of pink that you could find. You put a little white piece of paper in there to see it. Or I just like to say extra and credit, and then magically people do get very light pinks when they're doing titrations, and they start bringing their flasks up to me. Some of you did it, yes, it's just light enough. And we're going to talk about a very common sort of thing that you hear when people do titrations. The very common thing that most people will say when they do a titrations is like, I added 1 drop and it went like super pink on me. I don't know what the deal is. And we're going to explain why that happens. When you add just 1 drop, it goes like super pink. But we typically want to use an indicator that obviously would change color near the equivalence point. And for example, the titrations that they were probably yelling at you about, your equivalence point is probably near this range, in the colorless range, which is why they say you want the lightest color pink, because that should ideally stop you near the equivalence point and without you going over. Anybody have anybody that made them redo it if it was too dark? No? Yeah? Oh. All right, well, I'm going to explain why you really didn't need to do that in just a second, probably, as well. All right, so obviously, we'll talk about indicators a little bit later on in this chapter as well, but we would not want to use an indicator in this particular case that would turn way earlier than this, because you wouldn't see some type of color change. So when picking an indicator, as we did in that experiment the other day, they do have ranges at which they work. So you do want one where you could actually see the color change. So obviously, if it's in that part where it doesn't change color, it's not going to be very good for you. So let's talk a little bit about some different types of titrations here. The first type of titration we're going to talk about is a titration of a strong acid and a strong base titration. And that's like something like a little hydrochloric acid, which is a strong acid, plus some sodium hydroxide, which is a strong base. Going to do a little sodium chloride there, I think, and some water here, right? There we go. Okay. So what we're looking at here is a titration curve, and that's what you're going to be making starting today's lab and through next week as well. You're going to make these titration curves. The good news is, frankly, you're going to go past the equivalence point. So, you know, it's all right. In this case, you don't need to stop actually at the equivalence point. You're going to get the entire titration curve. And this is what a titration curve typically will look like in a lot of cases. And just for orientation purposes here, up in the burette in this example is the sodium hydroxide, and we're adding it to the HCl in this case. So in this case, we're obviously adding some base to our acid. And that is why when we look at this titration curve, our pH is starting low, because at the very beginning of titration, all we got is acid in there. As we start to add some base to it, there's going to be some reaction. So we start to get some of the pH starting to rise, and then we get to our equivalence point, and then we continue on. So let's take a look at really 4 different parts to this titration and talk about what's going on. So the very first part of this titration is actually kind of like before you start. So in this case, the very first part we're going to look at is before we actually add any sodium hydroxide to the flask in this case. So let's talk about what's going on in that situation. So at the very first point there, before any sodium hydroxide is added in this case, or any base is added, the only thing I have in my flask is the HCl, which means if I want to figure out the pH of my solution to begin with, how would I do that? HCl is what type of acid? It is a strong acid, which means it is going to 100% break apart into H plus and Cl minus, which means if I know the molarity of my hydrochloric acid, I then should know the molarity of my H plus, which means to figure out the pH of my opening solution here before I start the titration, pretty much I could go directly into the pH equation. So I could go right into the pH equation, and that will give me the opening pH of my acid that's sitting in my flask, my beaker, before I added anything to it. Yeah. You would in this case, because again, in terms of concentration, so for example, let's just say that this was 0.1 molar. It is a 1-to-1 relationship between these two, which means the molarity of the HCl would also be 0.1 molar. That's how concentration works. Basically, if it breaks apart into a 1-to-1 relationship, it's the same. Breaks apart into a 1-to-2 relationship, you need to multiply the concentration by 2 and so forth, basically. By the way, although we don't need it, the concentration of the chloride here would also be 0.1 molar as well, because it's a 1-to-1 relationship as well. So in this case, you could use obviously just the molarity of your HCl to begin with, because that's basically the concentration of the H plus in there. Other questions? We're going to talk about that in just a bit, yeah. So in this case, we're specifically talking about the strong acid. And in this case, because it is that strong acid, it will break apart and you'll be able to get the H plus concentration. So let's talk then about what happens as we actually do start to add some solution to it. So once we start with the very first drop of solution, I would say from the very first drop here all the way up to right before the equivalence point, we'll call that the second part of the titration. And in this case, we are going to get a reaction that's going to occur, right? And we will have to look at that reaction. So at this point, before the equivalence point, the reaction obviously will be the one that we wrote on the previous page there, a little HCl plus some sodium hydroxide. Going to give me some sodium chloride and some water in this case, yeah. So we do need to do an ice table here to figure out what is going on. And should I do this ice table here in molarity or moles? It definitely should be moles, because when you're doing a titration, you're doing nothing but continuously adding volume, right? Which means the molarity is continuously changing. That means we should do this guy in moles. So once again here, I'm going to just make up this number. I just made it out of my head is this number. I'm going to say that we started with here, I'm going to go with 4 moles of HCl. Okay, so again, I just made up the number for future reference. Just made that one up. If I am before the equivalence point, Should the moles of sodium hydroxide, which is what I am adding, should it be less than, equal to, or greater than the moles of the acid from before the equivalence point? Let's start with at the equivalence point. What are the moles? At the equivalence point, they are equal to each other, right? That's basically the definition of the equivalence point, which means if I'm adding sodium hydroxide, have I got to equal yet? Have not. I actually have less. Yeah. So before the equivalence point, the moles of the sodium hydroxide in this example, or the moles of the base in this example, should be less than the acid that you're starting with. Once again, making this number up, I'm going to go with 2 moles here. And I'm going to go 0. Now, because we're before the equivalence point, and because essentially I have less moles of sodium hydroxide, what is going to happen to the moles of sodium hydroxide? Will they get used up? Will they not get used up? They will get used up. At this point in the titration, my acid is like my excess reagent, and my sodium hydroxide is like my limiting reagent, right? It's going to pretty much get used up. You have plenty of the HCl there to take care of any of the base that you added. So in this case, we actually know the change. The change should be the moles of the sodium hydroxide that we added. So we will use the number. So -2, -2, and a +2 here. That means when we reach equilibrium, we will end up with 2 moles of this guy, nothing of that guy, and 2 moles of this guy. First off, any questions so far on the table here? All right, at this point, it is really good practice that I just did my table in moles. I'm going to convert these guys back to molarity here. This is going to be the total volume at this point, the volume of acid you started with in your beaker and the amount of volume of base you just added to it. So we would divide these guys by the liters to convert them back to molarity. And this obviously would be the total volume. And that would be the acid plus the base you added. All right. Now, at this point, we're still looking for kind of what the pH would be at this particular part of this titration. And I always tell people that, you know, you write this reaction, you make this ice table, you should use it to your advantage. So when we look at our ice table, we actually see that we have left over at this point pretty much 2 things, this guy and that guy. By the way, is that a buffer? It is not a buffer, yeah, because HCl is a strong acid, and you cannot have a buffer with a strong acid. So you do not want to lay up the pH Henderson-Hasselbalch equation here unless you're looking for an X. You don't want to do that. We want to look at and see what these things are. We have sodium chloride, which is a salt that we've talked about before. What type of salt is sodium chloride? It is a neutral salt, which means, frankly, I don't really care that much about it at all because it's not going to affect the pH, which pretty much means the only thing we really got left over at this point is our strong acid. And just like we did above, we can now go directly into the pH equation with obviously our concentration, which is why it's important to convert it back to concentration at this point. You're not rolling with moles and get the wrong answer here, yeah? So there are a couple places where it's okay, we should leave it in moles, but I would highly recommend not doing that. Convert it back to molarity, and you'll always be in good shape no matter what the situation at that point. So all the way from the very first drop of where you add your sodium hydroxide to right before the equivalence point, you need to do an ice table, and you need to do that ice table in moles. And the whole purpose of that ice table is to figure out what is your new concentration of your strong acid, because you should still have your strong acid all the way through from the first drop to right before your equivalence point, because it is actually the excess agent all the way through that sort of period of the titration. So 1 isotable moles convert it back to molarity and go into the pH equation. You'll be in good shape. Any questions on that there? All right, so that brings us to the next important part of the titration curve here, which is, we'll go with lucky number 3. Right there, which is our equivalence point at this spot. So let's first look at what is happening as we approach the equivalence point. We see on the curve here, which is sometimes described as an S curve, we are essentially heading pretty vertical, yes? So as we go to the equivalence point, we are heading pretty vertical in terms of our curve. So what that means is, does it take a lot of volume to change the pH a lot? If you're going vertical at this point, does it take a lot of volume to change pH? No is the answer, yes? And this is why when you do a titration and you had like 1 drop and it goes from like colorless to super dark pink, it doesn't take that much to change the pH. And that's important because when you're dealing with something like phenolphthalein, and you add that 1 drop and it works from pH of 8.3 to 10, that 1 drop's enough to move you to like a pH of 10, where you're going to see beautiful, my favorite color titration, dark fuchsia pink. Yes, that's a winner in that titration mover. But if you were really careful during your titration and you didn't open her up, like I used to titrate, just open it up, turn pink, shut it off, and go, cool, I'm done for today. If you're actually careful and you're adding drop by drop and pretty careful, and you just added 1 drop or 2 drops too many, it could change the pH a lot. In terms of the indicator, you see a very big change in color. But is there a big difference if you ended up right here versus here versus here, really? And if you go straight down, pretty much all those volumes are the same, which means if your teacher made you retitrate and you were really careful and you went too dark, you would have ended up with the same answer anyways, because he didn't really go that far in terms of the volume and stuff like that. The reason why most teachers will make you retitrate is if you titrate like me and you open it up and you really weren't careful, you could get the same pink color way over here, right? Which means you're quite far from the actual equivalence point. So if you were really careful when you're doing your titrations and you missed it by a drop or so, and it went really dark pink in the end in terms of the calculation, it really wouldn't have made that much of a difference. But if you really weren't careful, you could be way past it, and really why you see that dark pink. Any questions on that there? All right. So back to what's happening here at lucky number 3. I'll get rid of that now. All right, so at number 3, which is the equivalence point here, let's talk about the calculation that we got going on. So at number 3, we'll do the equivalence point. So we are going to get our reaction. And once again, I'm going to use my made up number of, I'm starting with 4 moles of this guy, which means obviously again here I'm adding the sodium hydroxide. So again, if I'm at the equivalence point in this case, how many moles of sodium hydroxide should I have? They should be equal to each other. So you should have 4 moles, yeah, of it, and 0 of that. That is basically the definition of equivalence point. You got equal moles of both of them, so they should be exactly the same. The good news on this one is you can't really pick a wrong number unless you pick 0, but you can't really pick a wrong number here. It's got to be 4 is going to be the change. That means when we hit here, we got nothing there, nothing there. Got 4 moles of this guy. We could convert it back to molarity using our total volume at this point. That means, again, if we look at this, the only thing we got left over here at the equivalence point is this guy. And you're now going to tell me that guy is what type of salt again? That is a neutral salt, which means you don't even need to do the calculation. The pH should be 7, yeah, or half a 7, there we go. So it should be a pH of 7 at the equivalence point in this type of titration. That is why sometimes a strong acid, strong base reaction is sometimes called a acid-base neutralization reaction, because pretty much you make water. Yeah, it's neutralized. It's 7, should be the pH at that point. Now let's talk a little bit about how we could figure out, while we're talking about the equivalence point here, how we could figure out the volume to reach the equivalence point. If it is not given to you, how would you be able to figure out the volume? Let's just say they give you the molarity of your base. They give you the molarity and volume of your acid. So let's just say in this case, you had for the HCl, the molarity and the volume. And for the sodium hydroxide, you have the molarity, and you want to know the volume to reach the equivalence point. How can I calculate that? Which is something you will have to do, because a lot of problems, they may not give you the actual volume. Yeah. Any ideas? Well, one way you could do it is your dilution equation, a little M1V1 equals M2V2 action, as long as it is a one-to-one relationship. If it's not a one-to-one relationship, you shouldn't use that, because it will not work. But you can use it for a one-to-one relationship. What I mean by that is a 1 mole to 1 mole relationship between your acid and your base. M1V1 could be your acid. This could be your base, and you could solve for the volume. Another way that you could do it is, well, you know that the moles of this guy should be 4 in this case. So you'll know what the mole should be. You also know the molarity of the base. So you could use molarity as moles per liter and solve for liters as well. So that's another way that you could figure it out as well. Or you could do it the old school stoichiometry way, which is take your liters of your acid times the molarity of your acid. Use the mole to mole relationship between the acid and the base. Oops, that's a mole. And divide by the molarity of the base. Which, by the way, that is basically what that does for you with a lot of less steps, is the M1V1 equals M2V2. And again, it only works really in case of the M1V1, because that's a one-to-one relationship. Again, if it's not a one-to-one relationship, you actually should do the calculation so you get the right mole-to-mole relationship. Any questions on it? 3 different ways that you could get the volume of the equivalence point. Okay. So the third part of this titration, as I mentioned there, and as we saw, should definitely be neutral. And we also see that it does go vertical near the equivalence point, and that's typically what you will see is, as you can see on this graph, kind of a jump in pH to the equivalence point, and then typically you get another jump past the equivalence point. So that is very commonly seen, and that's really why you kind of go vertical near the equivalence point. And it's really because you're kind of using up all your acid at that point. Now, the fourth part of the titration curve here is past the equivalence point to pretty much wherever you lay it up there and stop. That would be the fourth part of the titration curve. And let's take a look at what happens in that region past the equivalence point. So maybe you got indicator and it changed color, but it didn't stop you. You just keep going because you want the whole curve, which you will do. And let's talk about the calculation past the equivalence point. So the fourth spot there, past the equivalence point, we still have our reaction. Same reaction we've been looking at here. And just like before here, we should do this guy in moles as well. So again, I'm going to use the same number we've been using that I made up, which would be 4 moles of the HCl. That obviously is what we are starting with. We're still adding our sodium hydroxide here. Now that I am past the equivalence point, the moles of the base should be less than, equal to, or more than the acid. Should be more than the acid because we are definitely past the equivalence point. Again, I'm just going to make up the number of 6 in this case, and this would be 0. So what happens as we go past the equivalence point, and really why you see a sort of a jump in the pH, is there's a change that occurs. The limiting reagent in this case is now going to be the acid is going to be your limiting reagent. You got less of it than the base you just added. This guy is now going to be like your excess reagent. That means that the change we're going to see at this point in the titration is actually going to be the acid. I know that because if I chose the base, what type of number would I get? I would get a negative number, which you cannot have, yeah? So again, just keep it simple and like that. Don't take the bigger number, take the smaller number. That's going to be 0. That's going to give me 2 moles, and we got 4 moles of this. Once again, we could convert these guys back to molarity using the total volume, which again is how much base you added to your acid. Once again, if you're not sure what's going on at this point, we could use our ice table to help us. That is sodium chloride. That is sodium hydroxide. Is that a buffer? It is not a buffer. So a very common mistake people make is, I got 2 numbers. I know the Henderson-Hasselbalch seems like a really good fit. Let me put them in there. So this is definitely not a place where you should do that. We've talked about this guy a number of times up to this point, and it hasn't changed. Our sodium chloride is still a neutral salt, which means, once again, I don't really care about it. That really means here, what do I have left over is a sodium hydroxide, which is a strong base. Yeah. And because that's a strong base, it's going to completely dissociate. And that basically means we have the hydroxide concentration, not the H+, which means we could calculate the POH, and then we could get to our pH. So as you go past the equivalence point, frankly, you're just dumping base in there. So you got a buildup of hydroxide coming in. And again, that's why we see on the curve it jumps up high. Then it sort of levels off as all that hydroxide sort of builds into each other. And that will get you your hydroxide to your POH, and then obviously to your pH, you could subtract 14 to get you there. So past the equivalence point in this type of titration, you need to do 1 ice table. Once again, it does need to be done in moles. The purpose of this ice table at this point in the titration is actually to figure out how much of your strong base you have left over, the concentration of your strong base, so that you will have the hydroxide concentration, and that will get you to your POH and then to your pH. Any questions on that there? All right. So most titrations have these 4 sort of points: before you start, before the equivalence point, at the equivalence point, and past the equivalence point. So you should be able to calculate the pH anywhere along that pH curve. Are all points, if I'm really mad at you, yeah, it's all like 500 points along the pH curve. That's the next exam, just an empty curve. Give me all the pH points. No, I'm kidding. I don't want to grade that. All right, so let's try one here. Let's do, what do I want to do? Let's do let's do this one here. We'll do got an empty spot there, I think. All right, so let's say we what is the pH after 23.5 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar hydrochloric acid. All right, so calculate up the pH, see what you come up with. I'll do it as well since I made it up. So clearly we're doing a titration here. We're adding these together, which means that we need an equation, and it is the same one we've been looking at, which would be our HCl, strong acid, plus our strong base. Going to make a salt and water here, which again is our sodium chloride and our water in this case. I do need to do an ice table here, and this ice table should be done in molarity or moles. It should be done in moles, so we want to do that conversion. So for the HCl, we're going to convert our volume into liters, so divide by 1,000 or move the decimal point. Going to use the molarity there of our acid, which is 0.1 moles per liter. And that's going to give us our 0.0025 moles of our acid. So we'll put that into our table, 0.0025 moles. We'll do the same thing for the sodium hydroxide. Once again, we're going to convert this into liters. So that's going to be 0.0235 liters using the molarity of our sodium hydroxide, which is the same in this case. Will give us 0.0235 times 0.1. I'll just write it down here. It'll give us 0.00235 moles. And once again, 0 here. Any questions so far? Question I have is, am I before, am I at, or am I after the equivalent point at this point? You have just one more to go. You went before, and then you went at, then we could be after. Right? So we know by this, once again, we are starting with the HCl, right? We are adding the sodium hydroxide. So again, our ice table could be helpful here if we just think about it this way, right? If we're at the equivalent point, they should be equal, which means in this case, they are not equal. So we're not at the equivalence point, right? And what we're adding is less than what we started with, which means we're making our way to the equivalence point, but have not got there yet. So we are actually before the equivalence point in this case. So we're before the equivalence point in this case. Any questions on that? That also should tell us that the change that should occur here is which one, the HCl or the sodium hydroxide? Change here should be 50-50 shot. That's good odds. The change should be. Anyone? It should be the sodium hydroxide. At this point, it is the limiting reagent, right? This is our excess reagent. So that's going to be minus 0.00235 minus 0.00235 and a plus 0.00235 moles. That is then going to get us 0.0025 minus 0.00235 gets us 0.00015 moles of this guy, nothing of this guy. 0.00235 moles of that guy. Any questions so far in the ice table here? Now that I'm done with my moles part, I should convert it back to molarity at this point. My total volume is, we started with 25 milliliters and we added 23.5. I'm going to do it without the calculator. 48.5 milliliters there would be our total volume. That means we do need to convert it to liters. So we're going to divide this guy by 0.0485 liters. You could also do that one if you like. So that would get us 0.0485. Gets us 0.003093 molar. For the other one there, 0.00235 divided by 0.0485 gets us 0.04845, looks like, molar. Any questions on how I got the total volume there? All right, so once again, if you find yourself at this point not sure where you should go next, you should look and see what you got left. So once again, we got these two guys left. And once again, this is still going to be a neutral salt, which means we're not really even interested in this guy because it's neutral. That once again means that really the only important guy we got left over here is our strong acid. Which also means that this would be the concentration of the HCl at equilibrium, which means that really is, in this case, the H plus concentration here. And that is what we need to go into our pH minus the log 0.003093. Going to get us minus the log 0.003093. Going to get us a pH here of about 2.51 here, which is acidic in this case. Any questions on that one there? You see how we did. We added 23.5, which is about here. We had 2.51, so that's between those two numbers. Not too bad. It's pretty good. Yeah. You don't need to. You really don't need to put anything there if you don't want to, if you could recognize that it is. Other questions? All right. But I go through it just in case. Yeah. You don't zero it out. All right. So this is what we've been talking about, a specific type of titration. What we've just talked about in terms of how you calculate the pH anywhere along that titration curve is specific for a strong acid, strong base titration. And it is different when you start doing a different type of titration, which is what we're going to talk about next. So let's talk a little bit about the next type of titration. Maybe, there it is. So we're going to talk about titration of a weak acid with a strong base. And it is a little bit different how we sort of handle this. So we're going to look at acetic acid, which is everybody's favorite example. So we'll do some acetic acid, which is a weak acid. Going to react it with some sodium hydroxide here. Going to give us a little sodium acetate on that double displacement and a little bit of water action happening here. Kind of like the last titration in terms of orientation here. Up in the burette is going to be our sodium hydroxide. Down in the beaker, our flask will be our acid in this case. So our acetic acid will be down there. So once again, we are adding base to the acid in this titration. And that again is why we see we are starting with an acidic pH and ending with basic pH, heading in that direction. We also still see that typical S curve, and we also still see it going pretty vertical here as we reach the equivalence point in terms of its volume. We also see that jump to the equivalence point and also past the equivalence point, which is very common that you see. So let's talk a little bit about the same sort of 4 spots on this type of curve. So we'll start with the exact same sort of beginning spot, which is right here, number 1, before we start the titration. Now, in this particular case, at point number 1 of this curve, before we start it, what is the only thing we have sitting there in the beaker or flask? It is the weak acid in this case, yeah? So it is basically the acetic acid. How do I find the pH of a weak acid? What do I need to do? You pretty much can't go wrong in this place if you say an ice table would be a good way to do that. Yes, so that is like a Ka type of problem like we've done previously. So at the start of this titration, it is a little bit different to answer your question earlier. Because we are dealing with a weak acid here, it's basically a Ka type of problem. So in this case, we would take our weak acid, which is acetic acid. We would dissociate it into H plus and some acetate. And we would have our Ka. And we would do an ice table. And by the way, would I do this ice table in molarity or moles? I could do it in molarity because, again, at this point, we have not added any sodium hydroxide, which means we don't have to worry about the whole volume to volume type thing. So we would use the initial concentration here of our acetic acid. These guys would be 0. And we would go back to our x's in this case, minus x, plus x, plus x. This would give me my initial concentration minus x, x, and x. This would go into our Ka expression, which in this case would be H plus times the acetate divided by the acetic acid equals 1.8 times 10 to the minus 5, if you want the actual number. We would put our x squared in there. Our initial minus x equals our Ka value. We can make an assumption if it looks good. We can solve it however you want to solve it, quadratic, whichever way you want to go. But you would solve for x in this case. And in this particular case, when we do solve for x, as we can see from our ice table, x will equal the H plus concentration, which means you then can calculate the pH from it. So this type of titration is a little bit different because we are starting with a weak acid versus that strong acid. So it does require an ice table. That ice table is done in molarity. It is really just the Ka type problem like we did in the previous chapter. And you basically solve for x, which will give you your H plus concentration. And thus you could then put it into your pH at that point. Any questions on that there? So a little bit more work here up front than the last one there. So this is also why it's important to understand what type of acid or base you're dealing with so that you hopefully do the correct calculation. Yeah. Yeah, so pretty much that little list that we made the other chapter of the strong acids. If it's not one of those, it's probably going to be weak. And again, in a lot of cases, you will be given the Ka value, which is also a very big flag of, hey, that's a weak acid. So, that's what you want to look at. Other questions? All right, so before we start this titration, that is what you need to do to figure out your opening pH. Once again, the next part of the titration curve we're going to look at is after the first drop, which I missed. There you go. After the first drop to before the equivalence point there would be the second part of the titration. And let's talk about what is happening in that part of the titration. So second step there is before the equivalence point. And in this case, we would get a reaction, and a reaction would be, it would be our acetic acid reacting with our sodium hydroxide. So we'll have our acetic acid reacting with our sodium hydroxide, going to do a double displacement reaction here, going to give us some sodium acetate and some water here. So we do need to do an ice table. And of course, now that we have started our titration, we need to do that ice table in moles. So once again here, I'm going to make up just some simple numbers to look at. We're going to say we started with 4 moles of this guy. And once again, if I am before the equivalence point, the moles of my strong base here should be less, just like in the other titration. So because we have not reached the equivalent point, the moles of my strong base should be less. And once again, I'm just going to make up 2 and 0 here. That means the change part here in this type of titration should be the moles of which one? The acetic acid or sodium hydroxide? Not everybody at once. It is the sodium hydroxide, right? Again, it is the smaller number. It is the limiting reagent. So this is going to be -2, -2, and +2 moles here. That means when I reach equilibrium, that's going to be 2 moles. It's going to be 0, and that is going to be 2 moles of that guy right there. Any question on this sort of ice table here? Just like we did in the previous one, at this point, it is very good practice to convert this back to molarity using your total volume. So we'll take our liters and convert it back to molarity. And again, if you're not sure kind of how to get to the pH or what is going on, if you look at your ice table, we have this guy right there, and we have this guy right here. That's acetic acid and sodium acetate. Are they related to each other? Yes, they are a what? Right, which is also known as a buffer. Yeah, so you basically just created a buffer in this situation. So this is what occurs pretty much anywhere from the first drop of this type of titration to your equivalence point. You're going to make a buffer. And because it is a buffer, we actually have 2 ways that we can solve it. Probably the best and less chance for error, hopefully, would be to use the Henderson-Hasselbalch equation. So at this point, you could go in, making sure you put the base in the correct spot. In this case, which one would be the base? It would be. So that would be your base, and the acetic acid would still be your acid. So that would make sure those guys get in the right spot. Alternative to this, like we talked about with buffers, if you choose not to do a Henderson-Hasselbalch equation at this point, you could do an ice table. So you could still do basically the acetic acid breaking apart into H+ and acetate, where you would take your initial concentration here of your acetic acid from above. This would be 0, and most importantly, you would also, once again, need a number on the right-hand side here. Otherwise, you are not doing the buffer problem. You're just doing the weak acid problem. The rest of this would be some minus X's, some plus X's. You would solve for X. Once again, that would equal your H+ concentration, and then you could go into pH. So if you're a fan of the table, you could do that. If not, probably that's the better move there, just to go into the Henderson-Hasselbalch. They both will give you the same answer. By the way, the pKa value here I would use is the one from the weak acid. Yeah, so in this case, it would be the acetic acid, but you would use the Ka value from acetic acid here to convert it into the pKa value. Any questions on that? So as you can see, this type of titration, a little different than the one we did previously. At the beginning, we have a weak acid sort of problem. From the beginning of the titration, when you actually add some sodium hydroxide to before the equivalence point, you do need to do at least one ice table. The purpose of the ice table is pretty much get your concentration of your buffer. And then you have options. Then you could go into the Henderson-Hasselbalch equation, or you could go in to the ice table again, a second one. But you will end up with an acidic buffer pretty much all the way through there. That's also why it will kind of maintain the pH here for a little bit as you're kind of cruising through that section. You still have a fairly good buffer. As you continue to add sodium hydroxide, you're basically using up your buffer at that point. So you're kind of using up your buffer, and that's why you start to see towards the end of it, where there's not a lot of acid left in your buffer, a much bigger sort of jump and increase in the pH as it's blowing through that, basically. Question on that there. All right, let's see here. The other thing I guess I'll finish on is this. This is also what we were talking about a little bit earlier when we were talking about buffers, that although a buffer itself cannot be made up of a strong acid or a strong base, through a reaction, just like what we did in this part of the titration, you can actually make a buffer from a reaction of a weak acid and a strong base. Again, the buffer doesn't happen until you get to the end and there's no more strong base left over. So this is what is sometimes referred to as sort of making the buffer in the solution by adding a strong base to a weak acid. If you do it in the correct amounts, after the reaction is done, you will actually be left over with a pretty good buffer. Actually, you could actually make a pretty good buffer that way. But again, the buffer itself is not made up of the strong base. It is just used to make the actual buffer. The buffer that is made here is still the acetic acid and the sodium acetate buffer. Any questions on that there? All right, let's let that sit for a bit.